Today, we're diving into something truly special. It's a formula for pi that is just so elegant, so unexpected. You've probably never seen anything quite like it. All right, let's just jump right in and look at this thing. What you're seeing is a formula for pi, but it's wild. It's pi as the sum of two completely different infinite things. On one side, you've got an infinite series, a sum that just keeps going, and on the other, an infinite continued fraction, a fraction inside a fraction forever. How on earth do these two totally different concepts add up to exactly pi? It seems impossible, right? Well, that's what we're here to figure out. So, to crack this mystery, we're not going to start with the series or the fraction. Nope. Our journey actually kicks off with something much simpler, a single, really elegant integral. Here it is. We're going to call it z for short. And this integral, this is the key. It's the key that unlocks this whole identity. It looks pretty harmless, right? But trust me, hidden inside this simple-looking expression is everything we need to build that mind-bending formula we started with. Okay, so why this integral? What's so special about it? Well, it all comes down to the arctangent function. When you actually solve this integral, what you get is 2 times the arctan of x. And then when you evaluate that from 0 all the way up to infinity, you get, exactly, pi. So this confirms it. Our starting point, z, is really just a super clever way of writing the number pi. So here's our game plan. It's actually a pretty straightforward 3-step process. First, we start with our integral for pi. Second, we're going to split it right down the middle into 2 pieces. And third, this is the cool part, we're going to find a totally unique identity for each of those halves. This is really where all the magic happens. All right, first move, we're taking that integral, which goes from 0 to infinity, and we're just going to slice it right at x equals 1. This breaks our one big integral, z, into 2 new smaller pieces. The first part, we'll call it I1, runs from 0 to 1. And the second part, I2, picks up from 1 and goes all the way to infinity. Now check this out, because this is the really beautiful part. If you take that second integral, I2, and you do a little trick, a simple change of variables, letting x equal 1 over t, something amazing happens. A bit of algebraic shuffling, and it transforms into the exact same form as I1. It's perfect. So, get this. The big takeaway here is that these 2 pieces, these 2 slices of our original integral that looked so different, they're actually identical. I1 is exactly equal to I2. And think about it. If they're the same and they add up to pi, then each one has to be worth exactly pi over 2. This single fact, right here, is the engine that's going to drive this whole proof. Okay, so let's follow our first path. We're going to take that first integral, I1, and we're going to find a completely new way to write it. And you'll see this path is going to lead us straight to an infinite series. So the first thing we do is look at the function that's actually inside the integral. That little expression, 2 divided by 1 plus x squared, turns out it has a really useful property that we can totally take advantage of. Yeah, this function has a really neat trick up its sleeve. You can actually expand it into what's called an infinite geometric series. And when you do, you get this alternating sum of the even powers of x, all with a 2 out in front. Pretty cool. So what does that do for us? Well, since our integral I1 is just the integral of that function from 0 to 1, it means we can now integrate this entire series just one simple term at a time. It makes the problem so much easier. And boom, look at what we get. After you do the integration, out pops this beautiful classic series, the alternating sum of 1 over all the odd numbers times 2. This is huge. This is our first major piece of the puzzle. We've just shown that I1 is equal to this famous series. All right, that was path 1. Now for path 2, returning our attention to I2. Now we already know it's the same as I1, so its value is also pi over 2, but we're going to find a completely different way to express it. And this second path, this one's going to lead us to a continued fraction. Okay, so we know I2 equals pi over 2. Here's a little piece of trivia that becomes super important. There's another famous expression that also equals pi over 2. And that is 2 times the arctangent of 1. We can use this little fact to unlock a totally new way of looking at I2. And as luck would have it, the absolute genius Carl Friedrich Gauss came up with this stunningly beautiful continued fraction for exactly this, the arctangent of 1. I mean, just look at that structure. It's this incredible nested fraction with the squares of the integers just cascading down forever. So the logic is simple, right? If I2 is 2 times arctan of 1, then it must be equal to 2 times this magnificent continued fraction from Gauss. And just like that, we have it. That's the second and final piece of our puzzle. Okay, let's take a step back. We've followed 2 totally different paths, starting from 2 identical integrals, and we ended up with 2 completely different looking results. Now it's time to bring it all together. Time for the big reveal. All right, let's put the pieces on the table. From our first path, we found that our first integral, I1, is the same as this infinite series. And then, from our second path, we found that its identical twin, I sub 2, can be written as this wild, infinite, continued fraction. And now, let's remember where we started. Our original integral for pi was just I1 plus I2. The whole is just the sum of its 2 parts. Simple as that. So all we have to do now is substitute. Where we had I1, we drop in our series. Where we had I2, we drop in our continued fraction. And there it is, the grand finale. Pi, expressed as the sum of these 2 gorgeous and completely different mathematical objects. We've solved the mystery. You know, this whole thing is it's a stunning example of how completely different corners of math, integrals, series, continued fractions, can all connect in these surprising and, frankly, beautiful ways. It really makes you wonder, doesn't it? What other incredible truths like this are just waiting to be discovered, hidden in the language of mathematics?